Hi everyone, today we're going to be learning about trig identities. Now this section of work focuses on proving certain identities, usually looking at the left-hand side and the right-hand side of a trig equation. A trig identity is where you basically have a statement about the relationships of trig ratios. Okay, so to start off we're going to look at a special Pythagorean identity, sine squared theta plus cos squared theta equals 1. This is a very famous identity, and in fact a lot of identities stem from this one. So for example, if I take this identity and I divide everything through by sine squared theta, then what happens is I actually end up with another identity. And I'll show you what I mean. And this will be proved below so you can have a look in more detail. But what happens here is this sine squared theta divided by itself becomes 1. Cos squared theta over sine squared theta becomes cot squared theta. And 1 over sine squared theta becomes cosec squared theta. And this, in fact, is another identity. And you can make lots of identities by dividing through by one or the other thing. Okay. You also need to know these reciprocal ratios, which we already know those ones, but complementary angles. So sine 90 is the same as cos 90 minus theta. Cosec theta is the same as sec 90 minus theta. Angles of any magnitude as well is where we're looking at things like this, sine theta, sine 180 minus theta is sine theta, cos 180 minus theta is negative cos theta, etc. So what we're talking about here is if we look at our compass, our trigonometric rows, and we're thinking about all stations to central, we're thinking that if theta is in here, then this one here is 180 minus theta, this one in here is 180 plus theta, this one in here is 360 minus theta. Okay, so that's how you get all of these results here. So I wouldn't recommend necessarily memorizing all these. I would probably just make sure you understand and know this trigonometric rows diagram. Okay, so for instance, if I'm looking at this one here, sine 180 plus theta, which is in this, means in the third quadrant, means that you're going to have a negative value of sine. Okay, because only 10 is positive in that one. Remember the quadrants go 1, 2, 3, and 4. Okay, continuing on, here are some other really important identities based on the unit circle. So if here's my unit circle over here, I've got a distance of x horizontally, vertical distance of y, my point is xy, my radius is 1. So if tan theta is y over x, and that is sine theta on cos theta. Cot theta is the inverse of that. Okay, flipping it over. Continuing on, then we can see this special Pythagorean identity I showed you before, because what that means is if x squared and plus y squared is 1, remember y is sine theta and x is cos theta, so just subbing that in, that gives us the very important identity. These can be rearranged to give these identities. I showed you how we got the inverse of this one, but you can make heaps of identities based on this, and you can also rearrange them all. The complementary angles, cos 90 minus theta is sine theta, cot is tan theta, and cosec 90 minus theta is sec theta, but this is only when those values are defined, because in these two graphs you actually have quite a lot of asymptotes. Okay, so for example, cos 20 is the same as sine 70 to make 90, it's its complement, as are the other two. Remember what cosine, cosecant, and cotangent mean? They literally mean the complement of those things. First example here, we're asked to prove the identities. Okay, so what our goal is to do is to take what is on the left-hand side of the trig equation and transform it to what's on the right. So in this one here, where I've got tan x sine x, what I want to do is I want to write this in a different way. So instead of tan x, I'm going to write sine x over cos x, because that's another way to write tan x, multiplied by sine x plus cos x. Okay, and I want to rework this left-hand side to help me change it to become what's on the right-hand side. So just remember that's what we're doing here. So on the left now I've got sine squared x over cos x plus cos x over 1. And what I want to do now is I want to get myself a common denominator of cos x. Now, left I'm good. I've got sine squared x, and I don't need to do anything on the left because I've already got a cos x on the bottom. However, on the right, I need to multiply by a cos x because I've got a 1 there. So I put my plus, and then this would become cos squared x on the top. Now, I know my special Pythagorean identity says sine squared x plus cos squared x is 1. So I end up with 1 on cos x. And going up here, that actually happens to equal sec x. And that is equal to the right-hand side. And that's where I'm finished this proof. Okay. So just have another watch through that later and make sure you understand what went on. If not, bring your questions to me, please. In the next question, I'm doing a similar thing. I'm taking the left-hand side, so I'm going to go 1 on tan x plus tan x. And I want to make that look like the right-hand side. So 1 on tan x plus tan x over 1 is what I want to do. Okay, I want to get a common denominator of tan x. So I'm going to need to do nothing with the left because it's already got a tan x. On the right, I'm going to multiply the top by tan x, which gives me tan squared x. Now, 1 plus tan squared x is sec squared x from my trig identities. That's still over tan x. Now I can write that in a different way. I can write sec squared x as 1 on cos squared x. The line of a fraction means divide, the vinculum. And instead of writing tan x, I'm going to write sin x on cos x. To divide two fractions, I flip and multiply. So when I do that, one of the cos x's on the bottom cancels with one on the top. So I'm left with 1 on cos x sin x, which is 1 on sin x cos x, which is the right-hand side. Okay. So trig identities is really fun. They're kind of like a cool puzzle. I'm going to let you have a go at question C. Okay, let's have a look at this second example. It's a work example. It says establish the identity tan A is equivalent to sec A minus cos A. So in this one, I'm taking the left-hand side. Instead of tan A, I'm going to write sin A over cos A. This is multiplied, so sin A multiplied by itself is sin squared A. But I can rearrange sin squared A as 1 minus cos squared A using this here, the Pythagorean identity. So all they've done is move this cos squared A to the other side. Then I'm going to actually split the fraction up this time instead of getting a common denominator. It already has a common denominator. But splitting it up, I get 1 on cos A minus cos squared A on cos A. One of these can cancel, like this, which leaves me with sec A minus cos A, and that's equal to the right-hand side. Pretty cool, huh? Number 3 also asked me to prove the identity. Now, you should be able to look at this binomial product and think about what kind of binomial product this is. My goal is to show that it equals 1. So I'm starting you off on this one, but I'm not going to continue. I'm going to give you a chance to do it. So hopefully you recognize it's the difference of two squares. So we square the first one, square the second one, and put a subtraction sign. Okay, you keep going with that. The clue I'll give you is you need to rearrange cot squared theta. Go back up to the theory notes to help you do that if you don't know what to do. And then you should be able to get 1 from there. Okay. Number 4 is a bit of a different example. This one says eliminate theta from the following pair and describe the graph of the relation. So the first thing I'm going to do is I'm going to square everything, x and y. So I get x squared is 25 cos squared theta. Similarly, y squared is 25 sine squared theta. Then I would be getting to add them together. So x squared plus y squared is 25. And the reason I can do that is because from here cos squared theta plus sine squared theta is 1. And to describe the relation, I'm just going to write it's a relation, and this relation is a circle with center at the origin, or 0, 0, and the radius is at 5. Okay, so I'd like you to have a go at some questions from 6G. What have we learned about? We've learned about different trig identities, mainly stemming from the Pythagorean identity. And we've also learned how to eliminate theta, okay, and describe relations. Remember, our goal in this section is to always prove, and to prove we need to work it through using our knowledge of identities. Thanks everyone, see you soon.